Yeah, so I like to give BioSTEAM workshops, once in the fall and once in the spring. And I use these workshops as an opportunity to showcase new features in BioSTEAM. And these are not necessarily cutting edge features for new process systems, algorithms, or anything like that. It's more like features to make people's lives a little bit easier when they use BioSTEAM. I'm always trying to improve it with time. So I like to get people's feedback during the workshop and allow people to freely ask questions. And of course, if there's any questions that are too detailed, then we can always talk about those towards the end. All right, now for today's agenda, we're gonna go first introduce ourselves. If you prefer to remain anonymous, that's completely fine. But if you like to get to know folks from the community, then please feel free to introduce yourself. We'll start that right after we discuss the agenda. Then we'll go over the BioSTEAM documentation. So there's a lot within the BioSTEAM documentation and read the docs, and there's a high chance you haven't discovered something there that might be useful for you. Then we'll go into the tutorial. So I have new tutorials on thermodynamics, distillation, and multi-stage liquid extraction. So these are tutorials on very foundational aspects of chemical engineering as it relates to process simulation. And then we'll have a look at an example for bioproduct separation. And lastly, we'll end with questions and open discussion. All right, now I'll start by introducing myself one more time. I'm Yoel Cortes. I'm a postdoc at the University of Wisconsin-Madison. In chemical engineering, I'm working under Professor Victor Zavala. And I created BioSTEAM about 7 years ago, and I've been developing it ever since. And we've been using BioSTEAM to evaluate a whole range of different processes ranging from biorefining to waste plastic upcycling.
Yo, are you good for me to introduce myself?
Absolutely, Angus.
My name is Angus Shaw. I'm developing a company called Nonlinear CDR that's building a modular, self-scaling, financially self-sustaining carbon dioxide removal technology. And BioSTEAM is central to the techno-economic analysis of that technology. I'm incredibly grateful for everything, all the work you've done on this. It's a wonderful place to work.
This
Awesome.
is Ramesh Kalagnanam. I recently finished my second master's in chemical engineering from the University of Saskatchewan. My research had to do with producing biocrude from Canadian bark. This is my second innings as a graduate student. I finished all my work life and everything. I worked for 42 years. I started grad school again because I had a unfulfilled dream of aspiration of finishing a PhD also, which didn't get done, during my earlier years. Now I've been accepted. I'm from Raleigh. That's where I lived and worked. I am going back to NC State University. Starting January, I have a PhD admission at the Department of Biological and Agricultural Sciences there. And one of the professors there told me about BioSTEAM, and I don't know how I found myself on this mailing list, but I'm very happy. I'm happy to attend this and learn more about this. So thank you. That is a very brief introduction.
Thanks very much. Very cool. And congrats on your PhD admission. Wishing you luck on that. I'm happy
Thank you very much. Thank you very much.
to answer any questions throughout.
Yeah, I can keep going.
Absolutely.
I'm Karim Ben Hisham from RWTH Aachen from Germany. I'm not directly working on process design at the moment. I have some experience on working with molecular property prediction with graph neural networks and the likes. So I'm also interested to hear what thermodynamics you have integrated already into the package. Listening in mostly.
Gotcha.
My name is Vish. This is midnight here in Singapore.
Hi, Vish.
Hi. I and my team do a lot of LCA and TE, and we got to know about BioSTEAM from our colleagues. Illinois as an outpost and Create campus in NUS here. I know Owen pretty well, so just
very cool.
Yeah, understand more about BioSTEAM.
Are you a professor at NUS?
I'm a professor at ATU.
ATU.
I'm actually at the business school, but I do a lot of sustainability assessment with chemical engineers and food scientists and so on.
Okay, very cool, very cool. No, I love Singapore. I've been at NUS for 6 months doing a research exchange. Yeah, I even applied there to become faculty. Let's wait and see.
All the best. Yeah.
I think we'll go ahead and start. And if later on you have questions, feel free to introduce yourself during the question as well. All right. Now, before I get started, I'd like to make some acknowledgments and I suppose talk a little bit about BioSTEAM history. Let's see. So starting out with myself, right? I created BioSTEAM and I'm the developer indefinitely. So that just means I'll continue leading the development until I pass the mantle to someone else, if I pass the mantle. So endearing term that people like to use for these types of unofficial positions is benevolent dictator for life, but it's just a joke. I did my PhD with Professor Jeremy Guest. He was the grant acquirer for starting BioSTEAM and a real visionary and an amazing person to work with, of course. Now I'm a postdoc with Professor Victor Zavala. He's been a major supporter of BioSTEAM. A lot of folks in his lab use BioSTEAM and he continues to advertise it as well. And as well as have me continue innovating in the field of process simulation using BioSTEAM as a platform. Dr. Saran Bhagwat, who's now a postdoc, I believe at California, Berkeley. He's also continuing to develop some features in BioSTEAM, and we're both from the same lab with Jeremy. Professor Yalan Lee and Dr. Xingyi Zhang. We were both colleagues at the University of Illinois, Urbana-Champaign, back when I did my PhD, and they also continue to support the development of BioSTEAM. BioSTEAM was created as part of CABI, the Center for Advanced Bioenergy and Bioproduct Innovations. And since its creation, we've looked at a range of different pathways, going from cellulosic, conventional, and even engineered crops like oil cane, all the way down to diols, organic acids, oleochemicals, and biofuels. We have maybe 20 or more open source process models that are available in a repository called Bioindustrial Park. And I'll show you a link to that repository and guide you through it later on. Now, as part of CUP, the Chemical Upcycling of Waste Plastics here at UW-Madison, we're also using BioSTEAM to evaluate a number of pathways to upcycle waste plastics and as well as produce fuels, chemicals, and resins. BioSTEAM has a lot of different objects and features and classes, and it's easy to get lost within there, but once you start thinking about it in terms of its 5 core components, then it becomes much easier. So first we have the equipment for mass and energy balances, sizing, and costing. Every unit operation in BioSTEAM is a subclass of this abstract class called unit, which provides the entire framework for all unit operations. And units can have heat utilities and power utilities associated to them, as well as auxiliary units that might help in the design. The thermodynamic engine, so phase equilibrium, mixture properties, they're all calculated through the stream objects, which are inlets and outlets to unit operations. And these stream objects have access to the thermal data bank. If you've ever heard of Caleb Bell's thermal package in Python, you'd know how it has over 20,000 chemicals in the database with a lot of property correlations and simulation capabilities. So we leverage Caleb Bell's repository to create a thermodynamic engine for us. It also has automation tools for uncertainty, sensitivity, and optimization. And this is really the central feature of BioSTEAM, the ability to perform Monte Carlo-based uncertainty and sensitivity. So these work using a model object that has input parameters and output metrics, and they simply simulate the system at each scenario provided. And the simulation tools for process modeling, techno-economic analysis, and life cycle assessment, which is all done through this system object, and as well as a TEA object. And lastly, we have the Bioindustrial Park, which is a repository of community-led biorefinery models. Whenever there's a new biorefinery created in BioSTEAM, if I find out there's a paper out there, then I invite them to contribute their biorefinery to BioSTEAM with very simple tests to make sure that it runs. Okay, now this is a slide to remind myself to take a picture of us. Since I am on the faculty market and I want to advertise my service through BioSTEAM, then it would be extremely helpful if you turn on your cameras just for this picture. Okay, perfect. Got it. Thank you all so much. Now feel free to close up your cameras as well. Okay, and one more reminder, if you have a GitHub account, I cordially invite you to star BioSTEAM on GitHub, and that'll help increase the popularity of BioSTEAM. So on GitHub, we have this little button here to star packages, and that just means that you found BioSTEAM useful. It's like liking a post on Facebook. Okay, now let's go ahead and get started with the little introduction to the BioSTEAM documentation. So on the first page, we have the installation. If you haven't installed BioSTEAM, it's fairly simple, especially if you have a Windows. If you have a Mac, sometimes it can be a little complicated. So once you have a working Python installation, and we're right now on Python 3.12, then you can pip install BioSTEAM. Alternatively, you can also use the version on GitHub. If you have a working GitHub installation, you can download it using this line. Now, the diagrams that appear in BioSTEAM, those need an extra step. So to install the diagrams, the easiest way is to have Anaconda installed and then run this line. So conda install Python graphviz. And here are the instructions, right? So in case you forget, you can always come back to this. All right, now scientific papers, we have a range of different papers related to software tools, socioeconomic and policy studies, waste valorization, including upcycling of waste plastics, and biomanufacturing, bioproducts, and biofuels. A lot of the models that are in these papers are in the Bioindustrial Park. And here's a link to the Bioindustrial Park. All right, now let's go ahead and go to the tutorials on BioSTEAM. So here's the user guide. We have the beginner's guide, is very basic things, how to create a unit, how to connect, what are unit operation results, and as well as the preferences for you to view diagrams, the units of measure, and so on. We have more advanced tools for process development. So once you know more or less how to use BioSTEAM, then you might need to get a little more fancy to develop your process. So things like process specifications, where you add additional code to unit operations so that they're more flexible and more agile to your analysis. For example, maybe you want to adjust the amount of water coming into a mixer to achieve a specific dilution. So that's something that can be done by a process specification. We have inheriting from unit, so how to create your own custom unit operation model. Creating a system, because there's many different ways you can create a system, and it's nice to understand what's going on under the hood. TEA, LCA, and a few gotchas that are fairly common. We have detailed documentation on thermodynamics, automation for uncertainty sensitivity, some case studies. We'll be going over the bioproduct separation case study today. And finally, separations, which includes the thermodynamic fundamentals, which a few of you are interested in. And now these fundamentals are really not quite a lecture, it's more as it pertains to process simulation and BioSTEAM itself. I'd like to take a moment to go through the API reference as well. So this has detailed documentation in everything BioSTEAM, all the classes, functions, and so on. To go to the unit operations, there's this units tab here that you can click on, and it has a list of the different unit operations. So if I were to, for example, go to the pump, it tells you what are the input parameters to the pump, some examples. Or let's say I wanted to go to the flash vessel. all the input parameters to the flash vessel, an example, references, and everything related to the flash vessel. All right, so that's units. Let's hide that for now. We also have here for thermodynamics. If you want to see perhaps some of the methods for stream objects, for example, getting the heat capacity and so on, what are the units of measure, you can always go to here, the stream object. Or you can hit the search bar here, stream.u, for example, and you can find it. That's also a possibility. All right. Now, lastly, I want to open here the biorefineries tab. Here we have some documentation of the different core biorefineries. So for cellulosic ethanol production, for sugarcane, for corn, biodiesel, and ethanol production. So for example, maybe if I go to ethanol production over here, we have several functions to create systems for distilling beer, for ethanol purification after the beer column, or to create the complete system for ethanol purification. And to better understand how to use this, I encourage you to check out the Create Systems tutorial. And there's also examples or use cases within the Bioindustrial Park as well, where this is being used, and you might be able to copy that code and try to reframe it to the way you need it to be. Now, this is one of the least documented sections of BioSTEAM. And if you have any questions, I'm always happy to answer and improve the documentation as more and more people show interest. Now, lastly, I'd like to show you guys here this link to how to steam. So you can actually use BioSTEAM from your web browser through this binder. And what it does is it loads BioSTEAM on a server and lets you use BioSTEAM as Jupyter notebooks or as a console. I'm going to open the Thermodynamic Fundamentals tutorial. So as most of us are familiar with, thermodynamics can make or break a system. Sometimes we're operating at a certain thermodynamic range where mixture properties become very important. For the separations in particular, for vapor-liquid, liquid-liquid equilibrium. And we need to be able to not only understand key heuristics for property package selection, like for example, whether to use an equation of state or an activity coefficient model, or even ideal gas, but also be able to have a look at the behavior of our thermodynamics and make sure that they're reasonable compared to your experimental data. BioSTEAM estimates mixture properties as a molar weighted average of pure component properties plus the non-ideal contribution from interactions. So, for example, here we have the heat capacity of a mixture. It's a function of the composition, temperature, and pressure, and it's equivalent to a molar weighted average of the ideal heat capacity plus what's calculated from a mixture equation of state. So this is the excess heat capacity, which is a function of the composition, the temperature, and the pressure. Now, in BioSTEAM, you can have pure component properties estimated by your own correlation or by correlation in the database. And we have very rigorous correlations that are based on experimental data. But these are all open source, right? Now, if you do that, these pure component properties are not the ideal properties. So the way BioSTEAM is able to use these correlations and still add non-idealities from mixture interactions is by a little bit of math. So here in the second equation. So we take the pure component property and remove the XX property estimated by the equation of state. And this is equivalent to the ideal pure component property. And while this equation is not necessarily thermodynamically consistent, it provides more accurate estimates if you're using a very accurate correlation for pure component properties. In any case, this might be too much detail for a few of you. All you need to know is that regardless of whether you're using your own correlations to estimate pure component properties, BioSTEAM still adds that non-ideal interactions if you're using an equation of state in your property package. One last thing about mixture properties, there's certain properties that are not estimated through an equation of state. For example, the thermal conductivity. Instead, these are computed using mixing rules. For example, a simple molar weighted average is enough to estimate the conductivity for certain materials. And that's how BioSTEAM does it. Any questions on mixture properties before we go into phase equilibrium? All right, let's move into phase equilibrium. Now, phase equilibrium is very complex, so I won't go too much into detail, but just the necessary amount as it pertains to selecting your equation of state, which is important for process simulation. In phase equilibrium, it boils down to fugacities, this property of a mixture, which defines the tendency of a chemical to leave a phase. We need the fugacity of a chemical in an arbitrary phase alpha to be equal to the fugacity of the same chemical in the other phase. That's the phase equilibrium criteria. Now, fugacities can be computed in a number of ways, and one of the most rigorous fugacity models is this equation over here, where we include the pressure, the vapor molar fraction, and the fugacity coefficient, which accounts for non-ideal interactions in the gas phase. Then in the liquid side, we have the activity coefficient, which accounts for non-ideal interactions of the mixture, the liquid molar fraction, the saturation vapor pressure, which is the tendency of a pure component chemical to move from the liquid to the vapor phase, and a Poynting correction factor, which accounts for additional non-idealities related to non-condensable gases. So in BioSTEAM, you can actually select the level of rigorous that you want. So if, for example, you don't need fugacity coefficients, you can just assume ideal gas for the vapor phase. But if you need activity coefficients, then you can assume, for example, the UNIFAC activity model, which we'll talk more about soon. All right, any questions on fugacities and phase equilibrium? Now let's move into equations of state. The simplest equation of state is non-ideal gas. PV equals nRT, right? And it can be a good assumption when pressures are below 5 atmospheric and at high temperatures, particularly for hydrocarbon mixtures, which don't have much interactions in the liquid phase. But as we move into other ranges of operation, right, high pressures, low temperatures, or interactions, for example, if you have polar chemicals and they interact in the liquid phase, then you're going to need a more advanced property package. And one of the most common ones is the Penck-Robinson model, which just includes additional parameters that are a function of key properties of pure component chemicals. So the critical temperature, critical pressure, and the eccentric factor. Now, for highly polar mixtures with multiple functional groups, you can use the UNIFAC group contribution method to estimate activity coefficients. Now, you don't need to know any of the equations that I presented here, because what you do is simply tell BioSTEAM, I want to use this property package. And this is how it works. So we can start with defining the chemicals that we need to use. You can pass it by name. This could be a common name, could be a PubChem ID or a CAS number. It doesn't matter, but I do prefer to use common names to make it more readable, right? And you can specify the package. And we have a few packages that are defined in BioSTEAM. So here we have the ideal gas package, and we created an ideal thermodynamic property package. And these are the default methods that we're using. We're assuming ideal activity coefficients, ideal fugacity coefficients, no Poynting correction factor, an ideal mixture, and so on. This is one way to create a thermodynamic property package. Just pass the name and the chemicals. But you can also pass your own mixture object, your own method for calculating the different fugacity related factors. But that's not the current scope for this tutorial yet. Now, to create a Peng-Robinson thermodynamic property package, just say Peng-Robinson. I'll pass that as the package parameter. By default, I should mention activity coefficients are ignored. And this is because liquid activity coefficients using an equation of state has very odd behaviors depending on your operating range. And it's easier for the simulation to simply assume ideal, and we leave it up to the user to specify whether they require it or not. All right. Now let's have a look at the impact of choosing an ideal versus a Peng-Robinson property package. Here we're creating a stream. This stream takes as its first argument the ID. So we could have called it hydrocarbons if we wanted to, but I left it simple and just wrote none instead. Oh, and it also takes in the flow rates. Here I'm using the same flow rates for both the hydrocarbons under ideal gas and the hydrocarbons under Peng-Robinson. So I left it as a dictionary so that I can reuse those flow rates in both. But I could have also copied this one, pasted there, copied this one, and pasted here. And we can pass our thermodynamic property package. All right. Now here in this function is getting the change in the heat capacity between our two property packages as a percent, given the pressure and the temperature. So I'm using a internal BioSTEAM function to generate the data and plot this across a pressure between 1 to 10 atmospheric and a temperature between 250 to 400 atmospheric. So what we can see here is that the heat capacity can change significantly between an ideal gas and a Peng-Robinson property package. So this is especially true as at high pressures and low temperatures. Our difference in the heat capacity can be as high as 28%. So you can imagine how important this is for energy balances in your simulation. Now when we look at our phase envelope, and this shows the temperature in equilibrium, at a given pressure, yes. So under low pressures, we don't see much of a difference between the Peng-Robinson and the ideal gas property packages. But as the pressure increases, we start seeing a big difference. And that can impact not only our mass and energy balances, but also our separations. What's the yield that we're getting? The red is the vapor, the blue is the liquid. Given this mixture composition, at this pressure, right, and at this temperature over here, everything is a liquid. But as we increase the temperature, everything becomes a vapor over here. Does that make sense? If this is the first time you watch this diagram, you can get a little bit confused, just like I did. Okay, perfect. Let's move on here.
Repeat that, please? Could you?
Absolutely.
Please, yeah.
So,
thank you.
What we're drawing here is the vapor-liquid equilibrium phase envelope for this mixture composition, the one I specified in the stream. Now, at a pressure of about, let's say, 5 atmospheric, and at a temperature of 200 Kelvin, everything is a liquid, right? It's at the bubble point. But as we increase the temperature up to around 300 Kelvin, then everything becomes a vapor, and this is the dew point. So as we increase the pressure, the difference between the Penn-Robinson and the ideal gas bubble point and dew points become more and more different. Thanks for the question. Now let's have a look at ideal gas versus the UNIFAC activity model. So here we have a list of very polar chemicals: water, ethanol, isobutanol, and acetic acid, and we're assuming an ideal gas. And here we're assuming the Dortmund UNIFAC group contribution method. So now we're going to look at the impact of these two property packages on the phase envelope. So what we can see here is that the UNIFAC model shows deviations at low pressures and lower temperatures. This is because mixture interactions, right, chemical interactions in the liquid phase are very high at low temperatures, and they're lower at higher temperatures. Pressure does not quite affect the mixture interactions. In any case, these interactions become very important for highly polar chemicals, and that's why we use activity models. Okay, now we can also mix and match as well. So we can use the Penn-Robinson equation of state using a Dortmund UNIFAC group contribution model for the activity coefficients. And we can set this by passing this string as the package. And this is what we're actually creating. We're assuming the mixture properties are being estimated using the Penn-Robinson equation of state. The fugacity coefficient is also by Penn-Robinson. And the only difference is that we're assuming that activity coefficients are estimated through UNIFAC. So here we're plotting the phase envelope, right? The bubble point and dew points for this polar mixture. And we can see how adding that Penn-Robinson equation of state will lead to differences at higher pressures. So if you're operating both at high pressures with highly polar components, then you want to use both Penn-Robinson and UNIFAC. Okay, any questions until there?
Can I ask a question, please?
Yes.
Okay. Pardon my ignorance if my question is silly, but so you've shown these comparisons. So is there a way, I mean, has that been calibrated against what results you would expect in a given operation? So to see that, okay, if we use the combination, the final results are this, and if okay.
Yeah. So all these
and where
packages.
would one find such calibration studies?
There's a very rich history of calibration studies for all these property packages. So for Penn-Robinson, for UNIFAC, and so on, it's based on thousands of chemicals at different temperatures and pressures and so on. Now, we could always plot them here, and that actually might be a good idea to do in the future. But ultimately, so all models are wrong and some are useful. So the best way to make sure that you're using the correct property package is by comparing with experimental data. All right, now let's go into distillation modeling and design. Let's see, I'm gonna go ahead and skip some of the introductions over here and just note how distillation is one of the most widely used unit operations in the chemical industry, right? Applications in petrochemicals, pharmaceuticals, and biorefinery. So it's important to be able to model a distillation column. Now, there's many different ways to model distillation column. We have shortcut methods, which use simpler methods based on certain simplifying assumptions to make it easier to design and optimize a column. Now there's also more rigorous methods where you need to do the optimization yourself and decide many different design variables. So we're going to start with the shortcut methods and then use these methods as a way to initialize our rigorous distillation model. Now, for the most part, if you're doing a preliminary techno-economic analysis, or maybe some agile analysis where you just want to understand trends and sensitivities between your design and assumptions and connect them to your indicators of economic and environmental sustainability, many times the shortcut models are good enough and it won't change the conclusions of your results if you use a rigorous distillation model or not. And for this, you need a little bit of experience and trying things out as well. So, all right, let's start with the McCabe-Thiele distillation model. This assumes that the components have relatively similar heats of vaporization so that anytime 1 mole is vaporized, another mole is condensed. And this greatly simplifies the simulation of the column so that you can actually solve for it sequentially, stage by stage. Now, I'm not going to go into detail with the algorithm, just show you guys how to use this model in BioSTEAM. Now, this model only works for binary distillation, so only 2 components. It could be ethanol and water, for example. Here we're creating a stream, which it's meant to represent the beer coming out of a fermentation vessel. It has water, ethanol, some glycerol, and yeast. Now, in BioSTEAM, right, if you have an extra component, it just assumes that if it's heavier, then it'll all come out in the bottoms product. If it's lighter, more volatile, then your light heat, it all comes out in the distillate. So here we create the McCabe-Thiele unit operation. We can specify the light heat composition in the distillate and the bottoms product. And when we have a look at the results, it's as we expect. A lot of the ethanol is in the vapor and very little ethanol is in the bottoms product. And all of our glycerol and yeast ends up in the bottom product. Here's the results for the design. Cooling water, electricity for the pump, low pressure steam, theoretical number of stages, right? And then the actual number of stages for the rectifier and stripping sections. The purchase cost for everything, the trays, the reflux drum, the pumps, reboiler, condenser, and so on. And we can also draw here the McCabe-Thiele diagram. If you've ever seen it in a chemical engineering course, you know how this line here, the green line, represents your equilibrium line. And we just go from the bottom stage up like a staircase through the different stages until we reach our distillate. One more thing I should mention here, this diagram shows all the different components for the unit operation. Any questions on the McCabe-Thiele algorithm in BioSTEAM? Okay, if not, then let's continue on. Now let's move into the Fenske-Underwood-Gilliland algorithm for multi-component distillation. This one assumes that the volatilities, which is based on fugacities, right, are well behaved across the column so that we're able to assume a geometric mean between the bottoms product and the vapor product for the volatilities, and like that solve the column much more easily. This can be a big assumption if you have many different components with a lot of chemical interactions. It works better if you have hydrocarbons. And it works even better if the latent heat of vaporization is about the same between the chemicals as well. In those cases, it can be fairly accurate. All right, so here we're setting up our thermodynamic property package. We can pass the names and the package name to BioSTEAM's setThermo function to set the thermodynamic property package. Then we can create our stream object, set the flow rates of our hydrocarbons. This is all in kilomole per hour by default. we can flash it before it comes in. And here we create our shortcut column. Here we're specifying the light key recovery and the heavy key recovery. So 98% of our cyclohexane is recovered and 98% of our heptane is recovered in the bottoms product. Okay, now we simulate and have a look at some of the results. And it's as we would expect, most of our cyclohexane is in the vapor and most of our heptane is in the liquid. And most of our light key components end up in the distillate and the heavy key components end up in the bottoms product, with some amount being in the distillate and vice versa. So yeah, it provides a reasonable result. Now let's move into the rigorous distillation model. The rigorous distillation model actually solves all the detailed equations stage by stage. So you have material, equilibrium, and enthalpy equations for every stage and for every chemical. And given a number of stages, side draws, the location where you put the feed and side draws, then it leaves open 2 degrees of freedom. And those 2 degrees of freedom can be anything related to your condenser and reboiler. So you can specify, for example, the reflux ratio at the condenser and flow rate of your bottoms product as a fraction of the feed. These are 2 of the most common specifications for simulating a rigorous column. And we can also specify our pressure stage by stage, or just a single pressure for all the stages is fine too. So here we are taking our McCabe-Thiele distillation model and translating it into a rigorous model. And this is equivalent to creating the rigorous model using this code. So we're getting the results from our shortcut model and using it to specify a rigorous model. And we can see that the results actually match pretty well with our shortcut model. Now, here we're doing the same thing, but with the multi-component Pensky-Underwood-Gilliland model, or sometimes we just call it the shortcut column. And we can see here that we also get very similar results, but our temperature is more reasonable than the shortcut model. So in certain scenarios, it becomes important to use a rigorous model, especially this one. Any questions on rigorous versus shortcut methods?
Yeah, could you add a little more details on what assumptions are in the rigorous model? So, for instance, like liquid-liquid equilibria or something, I guess are not covered, or yeah.
Absolutely. So in this rigorous model, we do not have liquid-liquid equilibrium, at least not yet. It's not implemented in BioSTEAM yet. Instead, it has vapor-liquid equilibrium, and it makes no assumptions regarding like the latent heat of vaporization or volatility. It solves the column, all the material, energy, and equilibrium criteria and equations rigorously. So, for example, if we have 10 different components with 10 stages, the number of equations would be 10 times 10 times 3 plus the energy balances, which is another 10 equations for the number of stages. So that's, let's see, 310 different variables. So yeah, it can actually take a couple seconds to solve a rigorous distillation column, but it'll solve it to numerical accuracy, all the variables and equations.
Got it. Yeah, thanks.
Okay. One more thing I'd like to add is here you specify the number of stages, where is your feed stage, if you have any side draws as well. While that in the shortcut columns, you don't need to specify any of that, because the shortcut columns actually optimize your design of the column, while the rigorous one does not make any optimizations. If you want to optimize it, you have to add another layer of logic or code. All right, now here I'm going to expand a little more on the simulation algorithms. There's a lot of different simulation algorithms in BioSTEAM and out there for solvent distillation columns. There's the bubble point, sum rates, inside out, simultaneous correction. Feel free to read this later on. The main point of this section over here is to show you that BioSTEAM uses one of the most robust methods for simulating a rigorous column. It's the inside-out method, where we employ a surrogate model, or we fit a surrogate model, solve that model by optimization, then refit it again and repeat over and over until it converges to numerical accuracy. But these other models are included in BioSTEAM, and they do have their use cases if you ever need it. Now, we do have about 15 minutes left, so I'm going to breeze through the multi-stage mixer settler so we can talk about the bioproduct separation, which I think is the most exciting part of the tutorial. Alright, now multi-stage mixer settlers, they're used in a variety of different applications, from recovering a fermentation, an oleochemical fermentation product using a hydrophobic solvent, to, for example, washing biodiesel to recover glycerol and unreacted alcohols. So the main idea of this tutorial is that there's different design variables that we can play with. There's the amount of solvent coming in, and there's the number of stages. So if you have a high amount of solvent and a high amount of stages, you can get a very high recovery, but you'll get a high capital and operating expenditure, because your product will have a very dilute concentration, and you'll need to separate that from your solvent later on. And the number of stages will increase your capital cost. So in this tutorial, we're going to model the recovery of hexanol. Sorry, this is a typo. Which is a medium chain fatty alcohol, from a fermentation broth using a multi-stage mixer settler. And we'll push and pull the model to quantify the trade-off between recovery and concentration as a function of design decisions. So here we start with assuming 2 stages. Here n stages equals 2. And we're assuming an equal volume of solvent. So when we create our streams coming in, the feed and our solvent, we note the flow rates and as a volumetric flow rate. Alright, so we have first the feed and the solvent coming in at 2 different sides of the column. And then on the feed side is the extract coming out. And on the solvent side that's coming in is the raffinate coming out, because it's countercurrent. If you're ever confused about which order it goes, you can just copy an example and not think about it too much. Alright, so here we simulate, and we can see how we are recovering a great deal of hexanol using our hexene solvent. And a small amount of hexanol goes unrecovered. So this is for just 2 stages. The recovery is very high. Now I need to update this recovery to the exact amount. And now in this code here, we're just going to plot the sensitivity of our design decisions, of our cost, recovery, and concentration as a function of the design decisions. So here we're specifying the solvent usage and number of stages, updating the solvent flow rate and the number of stages, simulating, and then getting our recovery, concentration, and capital cost. And here we're collecting all the data for the different scenarios. And finally, we plot. And as you can see, as the recovery increases with the solvent to feed ratio, the concentration of our product decreases. Also, our capital cost increases with the amount of solvent we use, but not too significantly. Now, if we increase the number of stages, then it greatly improves recovery, but at some point, increasing the number of stages won't do anything. And it can also improve the concentration somewhat, but it'll greatly increase your capital cost. Okay, does that make sense? All right, we'll move on to the bioproduct separation. All right, so in this, oh, where's the diagram? The diagram didn't appear. Oh, no, it's right there. All right, I just had it later. So in this case study, we're going to be looking at the recovery of acetic acid from a dilute fermentation broth. Now, here's an industrially relevant flow sheet for the purification or dewatering of acetic acid. It employs some distillation columns and decanter where liquid-liquid equilibrium takes place. And it also has here a liquid-liquid extraction column, which we'll be modeling as multi-stage mixer settlers. Now, before going into the example, I'd like to talk about the thermodynamics. So when we look at the binary phase envelope for water and acetic acid, we find that as the purity of water increases, right, as we're distilling the mixture, then it becomes harder and harder to separate out the water and the acetic acid. So the blue line represents our bubble point, and the red line represents our dew point. At a given temperature, the concentration of our liquid and our vapor are going to be very close, and it's not feasible to use distillation in that scenario. In reality, water and acetic acid have what's called a near azeotrope. So it's not actually an azeotrope, and theoretically you can distill water from acetic acid, but the volatilities are so close that it's not feasible to do so. So that's why we use solvent extraction. Here we're using ethyl acetate to separate out the acetic acid. Now this is a ternary phase diagram where one side represents one liquid phase and the other side represents the other liquid phase. So in this side here we have a lot of solvent and some acetic acid and almost no water. And on this side we have a lot of water, almost no acetic acid, and almost no ethyl acetate. So as the composition changes, then our distribution or partition of chemicals starts to change. So in this area, we have liquid-liquid equilibrium. Outside this area, we do not. Okay, now if we were to separate out ethyl acetate from the acetic acid, ethyl acetate being our solvent, it's very easy to separate them both. So that's why we employ this combined configuration where we use liquid extraction and distillation to recover our acetic acid. All right, so here we are defining our thermodynamic property package. By default, it assumes unifac activity coefficients and ideal gas. We create our streams, and finally here we create our system. So here we have multi-stage mixture settlers. Here we're adding a specification, which just adjusts the amount of solvent we use to be a ratio of the amount of feed coming in. We have a heat exchanger. We have shortcut columns, and we're connecting everything together. All right, if you're new to BioSTEAM, you might be asking yourself, what's this? Well, this is a short way to create systems. What you do is you use this with statement. It's called context management in Python so that all your unit operations are logged into your system. Then we can simulate the system, and BioSTEAM will take care of solving recycle loops and all the mass and energy balances. All right, and here we're getting our installed equipment costs and utility costs and material costs as well. Now we can translate this to a rigorous design by using the mesh distillation object, which is a rigorous distillation model. And we can see that the results change somewhat. So here we had, let's see, 1.7 and 0.8. And here you have 1.8 and 0.9. So the results do change, and whether or not that's significant depends on what stage are you in the design and development process. If you are industry, those numbers are very important, so you want to use the rigorous model. But if you are doing a preliminary TEA, then it's not necessary to use a rigorous model. Okay, any questions on that? All right. Okay, so that marks the end of the workshop for what I want to present. I'm gonna open it to questions, and feel free to ask anything and everything. But of course, I'm going to allow for many people to ask questions. So try to ask relatively short questions, and then if no one else have questions, then we can keep answering.
So very quick questions. One is the recording of this going to be available?
Yes, it will.
Okay.
But after quite some time.
Okay.
It takes me a long time to edit, unfortunately. But
Okay.
I will try to get it on YouTube in January.
Okay. And second question is, you said that you conduct twice a year. The link for which, with this email invitation, you sent us a link, and that was for a 2024 workshop. So now you said you do spring and fall. So now we are in fall. Did you do one in spring 2025 for which
Yes,
the
yes, I
recording
did. But
can be made available, please?
it can be made available. Now, it's very similar to the past one. So that's why I haven't uploaded it, or that's why I haven't edited or uploaded it yet. But I will if I get
Okay.
enough nudges.
Thank you.
I have a question regarding the case studies.
Yes.
You mentioned the STRAP process, the solvent-targeted recovery of plastics. Is this package or module available in the code? Because I was looking for it and then I couldn't find it.
Yeah, no, you're right. It's not available yet. If it were up to me, it would be available immediately. It's a very solid model with tutorials. But what the team wants to do is publish this next paper where we're pushing and pull the model for a number of fancy optimization and supply chain analysis. And once that model is out, then it'll come with the code. So it might take maybe 6 months or so.
All right, that's good to know. And what assumptions are in there? So I assume you because it's with polymers, I guess there's some more difficulty. How is this represented?
Yeah. So for solids don't necessarily interact too much in terms of mixture properties, right? But for this one in particular, solvents, right? The polymers can absorb the solvents, and it creates all sorts of interactions and everything. So what we do is just a sensitivity analysis. We find out what actually matters for the economics. And it turns out that heat capacities is not too important, but it's all about that solubility. Now, at the same time, the viscosity of the mixture also has a big impact, but we're not able to, we basically have no idea how is the viscosity as a function of the solvent usage. So we just assume that there's like a feasible operation range, right? And see how that can impact our economics. And the main result is that it has a major impact, and we'll need to verify it later.
Cool.
So
Thank you.
yeah, we cannot do much without the data, but what we can do is find out what's the next step, find out the importance of the different pieces of data that we're missing.
Thanks.
That's a great question.
Can I ask one final question?
Yes, please go ahead, Norman.
Thank you. Thanks for the overview. It was very helpful. My question is there any option within BioSTEAM that we can change the fixed cost associated with each of the equipment?
Yes. It's not quite an option, but it's not that complicated. You just need to be a little bit familiar with Python. So one thing you can do is to subclass from unit operations. So even a distillation column, for example, you can subclass from mesh distillation. And what you'll do is replace this cost method. So you're going to define the cost method and set the purchase cost and any other factors associated to it. And that will override the costing. If you need to override the design, replace the design. If you need to override the mass and energy balances, replace the run method. Okay?
Thank you.
All right. If you have any comments, criticisms, something that you would have liked to see, I am always very open to input. So please feel free to email me your input. And what else? If you're having any trouble in BioSTEAM, I'm always happy to help, but I am just one person. So please give me like a week or two to reply. And I'm looking forward to seeing y'all next time. Thank you all so much.
Thank you very much.